Good afternoon, good evening to you all from a wet and rather chilly UK. This is episode 36 of Codebase Alpha, and it's part 3 of our investigations into the N-Audio library. And we're building a synthesizer just to investigate what we can do with this library and do a bit of kind of playing around with digital audio programming. It's quite an interesting subject. I'm getting quite into it. Still got an awful lot to learn though. What I have done is just plug this book. See if we can see this book. I bought this book, the audio programming book, which is an interesting read. About half of it is teaching you how to program in C. With the first kind of chapter is very general. The second chapter is audio programming based, so it's creating a lot of audio utilities. But after that, it gets the kind of difficulty factor in it is quite steep, and we start getting some quite complicated maths. So I'm having to brush up on some of my mathematics. But the whole kind of process of signal processing with N-Audio is to try and take away some of that complexity, but not all of it. So we are going to get quite mathematical at some point, but I don't intend to do an awful lot of kind of difficult maths on stream. Hopefully that we can kind of encapsulate that away into some classes, and also we can use some websites I'll recommend towards the end of the stream to get some open source algorithms that people have already written in different programming languages, C++ or Delphi or whatever, but we've got some sources where we can go and kind of find some solutions to the kind of problems that we're going to face in creating digital signal processing effects, which is kind of what we're going to end up doing with this. I am Sorky. Hello there. Welcome to the stream. Good to see you. I'm glad you could join us. I've not seen you in the stream before, so a very warm welcome to you. So if you haven't seen us before, we're a kind of a beginner-friendly stream, but we can quite ramp up into more difficult subjects. So today we're doing part 3 of our stream series on digital audio programming with the N-Audio library, .NET Core 3 and WPF, and we're building a synthesizer. So the end of last stream we ended up with a polyphonic keyboard, so we can play chords on our computer keyboard. So we're using the kind of the bottom 2 rows of the keyboard as our as just more than an octave of keys, and we've got a little GUI that we're building up, which has an octave selector on it, so we can select 3 octaves to play on. So it's working out quite well at the moment. Now, as a disclaimer, this is the first WPF application I've ever written. So when we come to doing UI work, it's going to be pretty basic, and I'm also not an expert on that. So that's not what the kind of point of the stream is. We're going to build some nice UI components on there, but they're going to be basic and not going to be very flash. Just utility components, so we can start to control some of the aspects of our synthesizer. So I'm Silky saying, nice to see you. Are your previous streams on your profile? Yes. So all my previous streams I archived to YouTube. So going back to episode 1. So I'll just pop my YouTube channel into chat. If you would like to subscribe to the YouTube channel, it's completely free to do so. You'll be notified of all videos that get uploaded, and they're usually loaded just about 24 hours after I stream, just to comply with Twitch's constraints on affiliates that I have to give Twitch 24 hours of exclusive content. So that's why it's 24 hours afterwards. Also, some more recent streams do stay on this site for about 60 days. So if you select the videos option on the tab across the top of the screen there, you'll see some of my past streams. So there'll be parts 1 and 2 of the synthesizer project, and also there'll be some work on the previous project, which was a Microsoft artificial intelligence conversational chatbot using the bot framework from Microsoft. Before that, we did some work with GraphQL. We also wrote an Alexa skill from scratch, so you can follow along and build your own Alexa skill from that. So we try to kind of be beginner friendly, in that we try to write things from the very start, rather than it being a learn to code stream. We're definitely not a learn to code stream, but you can kind of ask any questions as they pop up, and let me know if you're struggling on anything that we do, and I'll try and explain what we're doing. Okay, so today we're going to start off with some pull requests. So let's pop over first. I'll pop over into the code. So this is our application. We're in the synth wave provider class, which is the class that's currently providing the signal. So this is where the music is coming from. This is producing the sounds. Well, it originates the sound, so the waveform is coming from here. And if we just run this application up, you'll see there's not an awful lot to it at the moment. So we have a very simple GUI. We've got an on and off button, we've got an octave selector, and we've got a volume slider. So we can switch our synthesizer on, and we can select the A3 octave. So this is the note A, which is 220 Hertz in this case, and we have so a nice little synthesizer there. We're producing, that's a saw wave. We can we're going to have to be able to select what kind of wave we project. It's also polyphonic because I can play a chord. So for example, so hopefully you can hear that synthesizer playing there. So we got a completely polyphonic keyboard, and we can change the octave there. Okay, so that's about all it does at the moment, but we did take a little while to get there. And we've got a number of regulars who view the stream, and one of them, Fuel Snable, has given me a pull request. So let's go and have a look at that pull request over in our repository. So I'm Suki. If you want to see all the code we write, it's all open source. It's all available to you to go and have a look at, to copy, to play with, change, whatever. Skull, thank you for the subscription. That's very, very kind of you. Now let's give you some hyperspatial hype. What I'll do is just close down this window so we can see Alf in all his glory. So here's an infinite number of Alfs in a nice shader. This is a WebGL shader which our friend Fuel Snable created for us. So there you go. Thank you very much for the subscription. That's absolutely fantastic. So yeah, if you are interested in following the stream, just press that follow button and you'll get notified of when we stream. It helps me out. We're very, very close now to our goal of 200 followers. 196 at the moment. So any followers would be greatly appreciated. So let's go back to our repository. This is our GitHub repository. This is the repo with the synthesizer in it. There's a few notes here about what we've done so far. But if you note up here, we've got a number of outstanding issues, which is we're going to work on some of these issues today. We've also got this pull request. So if we go to the issues, the two issues which have been claimed here are the ones covered by the pull request. The first is a waveform visualization. So we're going to have something on our GUI which will represent the waveform that we're playing, and also a spectrum analyzer, so we can look at the range of frequencies which we're producing from the notes that we play. So let's go and have a look at that pull request. So add a rudimentary frequency visualizer. Actually, it's a bit more than that. So it covers both of those requirements. So it was the waveform visualizer and the frequency analyzer. So let's go and have a look at the codes that's been submitted. So so we've got 10 files changed. So let's go and have a look at what's changed. So we've got a new class, which is the amplitude visualizer. This is okay. It inherits or extends the framework element. So as I say, I am pretty much new to WPF, so we'll have to kind of work through this to see what it's doing. Okay, so we've got a dependent property. Okay. So here we're detecting a change of amplitude. Okay, and we yeah, so if it's null, we're invalidating it, and we've got a array of float array of the different amplitudes, because our amplitudes are floats rather than integers. We're using IEEE floating point 32-bit samples in our audio creation, which is what we want to be able to do to actually create effects later on. So we're going to be kind of building in some nice audio effects. So we're going to start off simple. We're going to put in a low pass filter. We're going to put in some tremolo. We're going to then extend it to maybe some frequency modulation with a low frequency oscillator. We're going to build delays. We're going to use a phaser. We're going to build kind of flanger. All these kind of exotic sound effects which you can find on modern hardware synthesizers. We're going to try and build those in software, and some of those get quite complicated in terms of the maths involved, as I was saying. But we're not going to kind of get bogged down in the mathematics of all that. Link Slumps, welcome to the stream. Good to see you. Nice to see you again. Okay, so let's carry on looking at this. So we've got a brush, a linear gradient brush, which is being used to draw. So this is the waveform, I believe. I think she was helping a guy with view and had to let him had to try to be respectful. Oh dear me. So yes, he was disrespecting you. Was he? That's a bit strange. If you were trying to help him, never mind. We didn't get. It's all sorts. It was being rude. And never mind. I do sympathise especially when you're trying to help someone. It is a bit of a problem sometimes. But you know, there's all sorts of people, aren't there? So yeah. So at least I mean, maybe if you pointed out to him that he was, you know, not acting correctly, which is on stream, Link Slumps. So I would hope that he kind of pulled his socks up and didn't carry on stream. Okay, yeah. So there could be all kinds of reasons why that kind of thing might happen, but you know, he could be tired, he could be frustrated, but still no excuse for losing your rag or being rude. Okay, so we've got a brush which we're drawing amplitude with. It's going to be red. Okay, it's going to be colourful, the look of it. And we've got an on render. Okay, so it's drawing. Okay, so there's going to be a black rectangle. We're going to draw colourful lines on it, both of it. And this is okay. So that seems okay. That doesn't seem a real change there. It's just a space or a blank line that's been removed and added. This is the interesting part. This is doing the frequency analysis. So, Cody Beard, welcome to the stream. Good to see you. Nice to see you again. So when we're dealing with analyzing frequency, we have to transform the signal that we're receiving, which is a time dependence signal, so it's amplitude varying in time. So what viewer did this code? So this is Fuel Snabel's code. Yeah, it's Fuel Snabel's code, and he's a very clever chap. So I'm quite happy with the code, but I just wanted to just give a quick look at it on stream. Yeah, so I was saying when we're dealing with a digital audio file, it's amplitude which is changing over time. So as you play the file or as time goes by, the amplitude of your signal is changing. When we need to analyze what frequencies are in that signal, we need to change from the time domain to the frequency domain. So we're going to analyze, instead of amplitude against time, it's amplitude against frequency. In order to do that, we have to do what's called a fast Fourier transform. And then this involves complex numbers. As you can see here, we've got a complex array here. Luckily, there are some mathematical support files in NAudio to help us with this task. And I'm not sure if Fuel Snabel's used those, but it does include those. I think it probably does, because he's including the DSP package here, the namespace here. So yes, it's Fourier transforms. Quite complicated mathematics, but you know, it's all kind of encapsulated within NAudio for us. So all we need to do is kind of utilize it rather than worry too much about the mathematics. Unfortunately, digital audio is mathematical. I was just saying, I don't know if you were here earlier, but I was showing this book that I have. I don't know if you can see it. It's called Audio Programming Book, and it starts off very simple with some teaching you C, and then it gets quite complicated mathematically. And that's kind of where I am at the moment. I'm reading the more complicated mathematical side of it. But so I've got some websites to share with you towards the end of the stream, which will kind of help. And if you want to contribute pull requests to this project, then there are some more meaty kind of projects which we can do to do some sound effects, some audio effects, and there's a couple of resources where we can kind of mine for algorithms to do that. So links assumption for differential equations, book in the cupboard. Yeah, you might want to get it out if you want to if you want to contribute. It's a lot of stuff like that. Okay, so this is implementing the iSample provider interface, which is the fundamental interface that we use to build up our signal chain. So a signal chain is when we're plugging together modules in a chain of processing, and our digital audio is going to pass through each of those modules and be changed or combined by passing through that sample provider. This is how we build up a much more complicated kind of audio signal. So we do this in kind of in stages. So we might start off with a source which creates a sine wave. We might pass that into say a volume control and into a mixer and mix it with other sounds. And that's how our polyphonic keyboard is working. We're using mixers for that. Feel Stable, welcome. We're just started going through the pull request that you put together. So thank you very much for submitting this. It looks really good. So as I say, we're implementing the iSample provider interface, and that has two requirements. The first is there's a property called wave format, and then there's a read method. And this is how we kind of plug them together. We feed in a sample, and then in the read method, this is where we change the sample. So we read in the data from the source, and then we can process it inside here. You can see we're doing a fast Fourier transform here. So this is where we're kind of transforming into the frequency domain from the time domain. And you can see here that when we're dealing with complex numbers, in this particular instance, we're only dealing with the real component x, but the imaginary component of the complex number, when we pump it into this process, is ignored. But we do have to deal with complex numbers that might come out of the process. This next part is part of the generated view model. So this is a generated file. Feel Stable originally submitted a PR with T4 transforms in it to generate our view model for us from a T4 template, which is working really well. So what does CS and SS stand for? Fouriers have S in their domain, don't they? Yeah, I believe so. That's right. So that's our model that's generated, and then we've got what's this? This is the more parts of the model being generated. Yeah. This is the template where we're adding frequency, amplitudes, and waveform properties. And that looks okay. And what we've got down here, so this is just changing the XAML so we're increasing the size of our window, which we're going to probably have to play with anyway, because we need much more screen real estate now for our GUI. And we're adding in the areas where we're going to visualize the waveform and the amplitude, the frequency amplitudes. And what we've got at the bottom, we've got, yep, so we're just changing that line there. And Yeah, we're just following some more code conventions. We're putting the underscores in front of the private variables, which is what I tend to like to do. Just correcting my coding standards there. Okay, looks okay. Uptime real-time data. So this is where we're going to be displaying on the screen the frequency analysis and the waveform analysis. Okay. And then we've got some changes to the synth wave profile, which we're going to be changing anyway during this stream. We've got our waveform visualization class. So this once again is extending the framework element. As per such, thank you very much for the resubscription. So that's most wonderful. So thank you. It's 2 months in a row. So that's absolutely amazing. So I'm just going to shrink this down, and we're going to have some infinite alpha hyperspatial hype. So thank you so much for that resubscription. That's absolutely it's amazing. So I'm really happy that you've done that. So thank you. Any questions, links to the Fourier transforms probably best answered by Fuel Snables if they have the class transforms in them. I don't know. I think we're utilising the code that's in NAudio, I believe, which we can have a look at. But it looks reasonably comprehensive from what I've seen of it. It does have kind of windowing functions and things like that in there to make the fast Fourier transforms reasonable looking. I think it's not the most. It's probably not the most complex implementation. Let's have a look at this. So once again, we've got a framework element with the waveform property. This is what we're kind of linking to back in the view model. Okay, then we do the change, and this is where we're drawing. On the black rectangle again. Okay, so it looks quite straightforward, doesn't it? All we're doing is Weetor, thank you very much for the follow. 197, we're getting so close, so thank you so much. Here's some Electric Alf hype for the follow, so thank you so much. This is another one of Fuel Snables WebGL shaders, which is so much fun. Fuel Snable, a subscription, thank you so much. That is amazing, so thank you. Thank you so much. There's some. Let's just shrink that down again. You don't see Alf so well against the white, so there he is, infinite Alfs. That's so much fun, isn't it? Our little alien buddy there replicated millions of times. Okay, so let's approve this change. So thank you so much for this PR. Looks amazing. Submit that review. Okay, and we're going to merge that into our branch now, and then we can have a look and see what it looks like. Okay, looks like we merged. Okay, let's go and grab that code. So there we go. I'm pulling that down. So it looks like we've got that code now. Let's go and just have a look. Yep, looks like we have. We've got the amplitude visualizer and the waveform visualizer. Let's fire it up and see what we can see. Okay, so we've now got a much bigger screen. We're going to have to make it deeper, but we've got a nice screen. Let's turn our machine on, and then we'll play the note C. So that, remember, this is a saw wave, or it might be a square wave actually. So you can see there as we're playing that. Let's turn the volume down slightly. We can see that we've got a lot of high frequencies in that noise. So let's see what type of note we were playing there. Yeah, we're playing a square wave, which is what we could see. So let's change that to be a sine wave. And let's see what we see with the visualizer that way. Turn on and we'll play note C again. So there we go. And if we play a chord, that's quite nice. So we can see that we're very much in the low frequencies there on the spectrum analyzer. And if we move up, so if I go and we change up an octave, so very nice. So thank you so much for that, Fuel Snowball. That's wonderful. wobbly, yes. We can probably say, as Fuel Snowball's PR says, it's rudimentary, but I really like the frequency analyzer, and maybe we can play around with the representation of the waveform. But it's fantastic for now, because especially with the frequency analyzer, because it does kind of show us a few interesting facts. So if we move, say, to something like a sawtooth wave, which would be this one at the bottom here. Let's change to a sawtooth and have a look at that. Switch on. We'll go for the middle octave. Let's play a C. We can see our sawtooth there, but can you see that when I other than the notes, you can see that the peaks are here. You've got a lot of harmonics, a lot of very high frequency harmonics in that. And what we want to do is introduce a low pass filter into that to try and get rid of some of those more annoying, harsh sounding harmonics. So that's one of the things we want to do today, is to bring in a low pass filter. And these are the kind of things that we can kind of build up. We can start to create lots of controls on this surface here, where we can add in high pass, low pass, notch filters. We can start to put things like, so we're going to have a tremolo effect we're going to do today, if everything goes well, that is. We want a delay so we can get some echo. We may want some reverb, maybe we want a flanger and a phaser, just to kind of ramp up the different kind of sounds we can make. And then we want to build in some musical instruments, so we want some presets. It's where you can say, I want it to sound like a church organ, and it will set the synthesizer up to be a church organ, or a harmonica, or a piano. Piano is going to be quite difficult, I think, or a trumpet, or whatever we can do. And I'm looking for some kind of PRs for people out there who are interested in trying to recreate musical instruments. Once we get that far, once we get to a situation where we can create presets, it'll be really good to have those kind of those people submit musical instruments for the synthesizer. And who knows how far we can take this. I mean, it might not fly for very long, this project, but it could go on for quite a lot of time. It's quite an interesting subject with a lot of depth to it. Let's turn off and let's go over to our GitHub. So on the issues, we can now close some issues. So we can close the spectrum analyzer, because we've got one of those. So we'll close that issue. Implemented by PR. I think it was PR number, that one, number 3. So comment there, and we'll close that issue. Okay, so Fuel Snowball has already contributed to the project, so he does appear on as a contributor. I use a bot called All Contributors, which creates these contribution badges with the emojis as saying that you've contributed code and ideas and feedback to the project. So if you do contribute, you will get full credit for your contributions. So we're told, does this program make the sound or detect listen to it. So it generates the sound currently with a wavetable. But one of the things we're going to do today is actually ditch the wavetables, and we're going to replace those with signal generators. So N-Audio does provide a signal generator class, and we're going to initially use the out-of-the-box signal generator class, and then we're going to kind of implement an extension to that to enable us to have frequency modulation. So one of the things that we don't have at the moment is any kind of frequency modulation capacity. So we can't put a low frequency oscillator in there and give some vibrato. We're going to do tremolo today. With tremolo is something different. Tremolo is we're going to put a low frequency oscillator on the volume control, and we're going to vary the volume up and down. But we need to be able to get at the sine wave formula in order to frequency modulate that. And with wavetables, it's not quite so easy to do that, because you don't. The wavetable has all the samples for a 1 cycle of a 1 Hertz sine wave, or 1 Hertz square wave, or triangle wave, or whatever, and so then frequency modulating that becomes a bit more difficult. We're going to kind of rip those out. I think FuelSnable pointed out in the first stream for this project that we have enough computational power that we don't need to fall back to lookup tables. So we're going to try that. The tables probably can do it, but it's not obvious to me exactly how links lumps, because the way we create frequencies is by reading the wavetable differently. So that the wavetable is a 1 Hertz sample of a single cycle, and then we kind of read it in different chunks. So frequency modulating that reading, it looks quite complicated. It's probably possible, but I'm not exactly sure how to do it. But I'm pretty sure I will be able to work with the actual signal generation formulae, the mathematical formulae, to vary the frequency modulate to include frequency modulation. Mainly because those formulae are available on the internet and in book. So we're going to ditch that. So that's one of the things we're going to do today. So what was the other thing? It was the waveform visualization. So we can close this one. So implemented. I think it was number 3, wasn't it? Yeah. Implemented. Let me come into that. Close that one. So that's 2 issues closed, which is nice. So we're down now to 11. Okay, so what I'd like to work on the stream this evening is ditching wavetables in favour of single generators. The order may vary, so we're going to do that one first. Then we're going to create sound envelopes. So it's called the ADSR envelope. So that ADSR stands for attack, decay, sustain, and release. So that's what give our notes character. So for example, when you press a piano key, you'll notice that the note comes on very sharply, but then tails away slightly. At the moment, our keys are like switches; they're on or off. They don't have any kind of character to them. For example, when you play a church organ and you hit the key, then the sound of the note kind of builds and then tails away quite slowly, relatively speaking. So wavetables, Hertz, frequency modulators, signal generation. Yes, those are words. I know words. Yes, it's a minefield of terminology. So I'm reasonably happy with a lot of the terminology. I kind of understand it in my own head. So when we talk about aliasing, I kind of understand what it is, but whether I can explain it on stream is another matter. So I might flail around if you ask me what aliasing is. But I kind of understand it conceptually. In terms of sample rate, Nyquist frequency, sampling theory, I've got a rudimentary grasp of those concepts. So we can talk about bit depth, we can talk about sample rate, that kind of thing. Yes, so Hertz, it's cycles per second basically. hertz. So it's number. So how many? So for example, our program is sampling the digital audio at 44,100 hertz. So that's every second. It is taking 44,100 samples, digital samples of the amplitude of the wave at those intervals, and that's basically CD quality. And the reason why we're using 44.1 kilohertz relates to that's what CD quality sound is, but also to what's called the Nyquist frequency. The Nyquist frequency is basically it's half the sampling rate. So the sampling rate is 44.1 kilohertz. So the Nyquist frequency is 22,000 hertz, 22 kilohertz, and that is basically just above the rate, the highest frequency the human ear can detect. So what the sampling theory says is that you need to sample at least twice the frequency, the highest frequency that you want to include in your samples. If you don't, then you get what's called alias artifacts, and these are false frequencies generated by the fact that you're not sampling quickly enough to detect the actual high frequency. So, which is another reason why we want to have a low pass filter in our setup, so that we don't suffer from having all those high frequencies. Linksum says, can you post in the Discord the videos to watch on Udemy for this? So it was Pluralsight that I did the courses on. So I've done a couple of courses on Pluralsight. One is Digital Audio Fundamentals, which basically goes through all the terminology and talks about sample rate, sampling theory, Nyquist frequency. It talks about the concept of mixers, about digital effects, volume controls, metering, frequency analysis in terms of spectrum analysis, and fast Fourier transform and things like that. So I will put the links in Discord, yes. If you remind me towards the end of the stream, I'll make sure I do that before I pack up for the evening. I'll also give you a couple of links to sites of interest. So I'm looking for contributions on this. So if you want to do, for example, here's one: add a graphic equalizer. That might be a nice one for someone who's interested in looking at the kind of adding that feature and be able to look at the different frequencies that are being generated by the synthesizer. And it could be as simple as a 3-channel equalizer with bass, middle, and treble, or it could be much more complicated, to have many more graphic equalizer kind of sliders on it, so we can vary the volume or the amplitude of signals that are broken down by frequency that way. Yeah, so Linksums do fork the project and have a look. So there's a couple of other things. My photograph is against some of them, just because I think these are the ones I'll probably do on stream. But if you want to grab some of them, just let me know what you want to do in Discord, and we can decide if that's something I've kind of got earmarked for on stream. At the moment, there's kind of notionally I'm going to do them on stream, but it could be that that it might be better done. It might be better done by PR. So, for example, a phase shift effect. This is available if people want to grab that one. But be warned, you're going to need to do some research about how to actually code the algorithm for doing phase shifting. Sub-oscillators might be an interesting one for them to do. Delay effect, I've got some ideas about how to do that. Waveform select, if you want to do a bit of GUI stuff for me, creating a waveform select, let's say select between sine wave, saw wave, triangle wave, whatever. So there's options. And then a bit later on, when we start looking at presets and instruments, then people can start contributing instruments, and we'll add different ideas. And I'll continue to build this list up as I kind of work my way through all the background material I'm reading on all this, and we start to kind of think of what we can do. Okay, so let's look at the next thing. So I think this one here, which is ditch wavetables in favour of signal generators. We'll tackle this one. And the reason why this is of interest is because it kind of enables us to work on some other issues. So we've got 3 open issues this was going to be a bit of an enable for. So there's the waveform selector, the low frequency oscillator for frequency modulation. I believe we'll be able to do it a lot easier if we ditch wavetables, and also one we're going to do tonight, which is the sound envelopes, so sound shaping. So I think it's not exactly required for that. We can do this with wavetables as well, because it's just basically shaping an amplitude profile, an amplitude envelope. So it's not dependent upon going to signal generators. But I think it's one we can excuse me, we can do tonight anyway. So it said we're using wavetables limits, or at least appears to me to limit what we can do, especially around about doing the frequency modulation. So we're going to remove that and replace them initially with the N-Audio signal generator class, and then later on we're going to customize the signal generator class to add low frequency oscillators in there. So let's tackle that, shall we? Okay. So this should be relatively straightforward to do. So currently, when we generate a note, we create instances of this class. So basically, we tell it what note it is. So the notes range from 0 to 16. So 0 is the note A, and then 16 is also the note. It is going to be 16 is going to be C, but an octave in the next octave. So that's how we kind of calculate the frequency. So we use this formula here. So N is the note number. So for when N is 0, we're on the note A, and in this case the base frequency is 110 Hertz. So this term here becomes 1, and the frequency of the note A is simply equal to the base frequency, which is 110 Hertz, which is the note A2. So it's the note A in the second octave on the piano. That's a kind of a low note. So that's how the class knows what frequency it is, based upon what note number we send into there. So we send the note number in here. Sample rate we fixed at 44,100, which is, as I say, that's the CD quality sampling rate, 44.1 kilohertz. And we set up ourselves with a wave format of the IEEE floating point, 32-bit floating point samples, which is what we use inside a iSample provider implementation. And this is the read method. So there's 2 things as I say, when we implement this interface, we need a wavetable, a wave format, which is here, and we need a read method. And this read method is basically, if you look at it, it's very similar to kind of a memory stream read method, except the buffer is floating point rather than being an array of bytes. Otherwise, if that was a byte there, the signature would be identical to an ordinary stream read. And this is where we can do our processing in this read method. In this case, we're simply kind of creating the sound. So we're taking the samples by looking at the wavetable, and it's the way we kind of create the frequencies is by varying the phase step here. So we're going to kind of get rid of all that really. So the best thing we can do is actually pass into our constructor the kind of wave we want it to create. So this is we have in N-Audio a signal generator type, which is going to be our wave type, and we're going to default that to a signal generator type. a sine wave. Sine. Okay. So we need to bring in a namespace for that, which is an audio wave sample providers. Okay, there we go. So rather than creating a wavetable like this, we're going to use the signal generator. So what we need is a source. So we'll create a private read-only, and it's going to be a signal generator. I'm going to call it source. And in here, we're going to say that our source is going to equal a new signal generator. A signal generator takes Keenan, thank you very much for the follow. That's fantastic. So we're now 198. It's only 2 away from our target. So thank you. Here's some Electric Elf to celebrate. Thank you so much. It really, really warms my heart when people do take the trouble to follow. So thank you very much, Keenan. That's much appreciated. Okay. So as you can see, our signal generator takes a couple of parameters. First is the sample rate. So that's going to be underscore sample rate. And then it takes a number of channels, which is simply our channels. So this is mono, you'll notice. Single channel. We'll probably work on a mono to stereo converter, and then do some kind of fun with panning within the stereo field, so we'll be able to kind of have the sound coming from different sides, different speakers, or like 3/4 of it from the left and 1/4 from the right, or whatever. But even things like panning is relatively complicated. Luckily, there are some classes in N-Audio which help us do that and work with things called the Mu law and the A law, and the theory of panning is relatively complicated. Surly Dev, welcome to the stream. Good to see you. Thank you for joining. Okay, so signal generator has a number of properties. It obviously has a frequency, which we're going to set to the frequency which we've from this class. It has a type, and that is going to be our wave type, and it has a gain, and the gain we're going to set to 100%. So the volume control is going to be done post mixing, which we've already got that kind of feature in there. So I can show you that when we come to kind of wire this up a bit. So that's our signal generator. Because on our source, and we no longer need any of this code here. So we can just lose all that. Okay, and this becomes nice and simple as well, because we no longer have to worry about phase steps. So we can lose that. We've got phase step up here now. Okay, and in our read here, all we need to do is say that all we need to read from the source buffer. So so we'll say that samples are going to come from the source. So we need to pass in the read method of that, and obviously we want to have the same parameters that we pass into this read method. So the offset, the offset, and the count. The count being the number of samples we want to read. Set. There we go. And then here, all we do is say that our new buffer is going to be equal to our this is samples. Okay, our new buffer What's that going to be? So we don't need anything yet. So we're going to need to process that. So that can be count. That should do actually. We'll just call it sample, shall we? Yeah. Okay. So that's basically just saying that when we read from our class, we're actually really reading from the source, but we're going to want to do some processing with it, so we need to keep this piece of code in place. Okay, so let's give that a run and see what happens. So let's just save that, pop over to our view model. Okay, so where are we? Key down, there we are. So here we need to pass in the type of wave we want to produce. And what we'll do is simply pass in a signal generator type sine, just a boring sine wave to begin with, just so we can see it working or hear it working. Okay, and this is where we're going to have our opportunity to have a GUI control which will change the type of wave that we're producing in the synth. So let's save that and run it again. Switch on. So we're expecting a sine wave. So let's play C. Now, one of the problems with this, I don't know if you can detect it on stream, but as I press the keys and move between notes, you'll probably hear a click. So if you listen very closely. Okay, so that click is a bit of an artifact due to the fact that our kind of attack and release on these notes is like instantaneous. So we get in that click, that artifact in there, and what we need to do is kind of shape the envelope of sound that we're producing so that it kind of loses that click, and we kind of blend the notes together a bit better, because a real analog instrument doesn't have that kind of clicking. If we go up an octave here, so we haven't gone up an octave, have we? We're not shifting octave, we're still staying down. Okay, so we need to fix that octave shifting's not working. So let's have a look at that. So we're passing a bass frequency in there. Right. What's wrong with that, I wonder? Let's go and have a look at our synth wave class again, so we can get rid of a few unused variables here, just to make our file a little bit shorter. Okay, so here's our bass frequency. We set it to 110. Bass frequency should be being controlled. Frequency equals frequency. Okay, I think that's what we need to change. We need to look at our frequency control there. Okay, so base frequency equals 110. So we need to kind of fiddle with this a bit, I think. Let's get rid of that, and let's convert that to a property with a backing field base frequency. Okay, so this should be okay. Return the base frequency. So here we want to set that, and then if we've got a source, if that's not null, then we can set the source frequency. The source dot frequency should be equal our frequency, and the frequency is calculated from this formula below. So that should give us what we need, I think. Let's give it a go. So let's make sure we haven't broken anything. That clicking is quite noticeable. So let's shift an octave. Okay, that's working. A nice visualization there. Okay, so that's pretty boring, isn't it? The old sine wave. Let's have something more interested. Kind of keyboardy, yeah. But it's a bit boring. A sine wave is always going to be a bit boring. So let's have a different wave. So let's choose a sawtooth wave, which is a bit more kind of aggressive, and we'll see some of the features of a sawtooth wave because we've now got the frequency analyzer. Okay, let's start up. So here's C. So you can see nicely it's a sawtooth, very, very buzzy. Lots of high frequencies, lots of harmonics in there. Here's the fundamental down here. All these harmonics are appearing all the way down there. So that's why it's so buzzy and harsh. But it is a bit more synthesizer-y, really. So that clicking is the next thing we want to look at, I think. So how can we do that? Well, there's a couple of approaches. One of which is built into N-Audio. Let's pop over to the N-Audio repo here. This is the N-Audio repo on GitHub. And under waves and sample providers, there's what's called an ADSR sample provider. This basically does what we want, except if you read the code, it's not quite as flexible as I'd like. So in this piece of code, we basically get to set the attack, the A part of ADSR, and the release. So that's in seconds. But the sustain level and the decay we don't get access to. So what am I talking about when we're talking about ADSR? So I'll see if I can draw something. Let's bring up Paint. Okay, let's have a canvas to draw on. And we'll draw some straight lines. And what size brush shall we have? Let's have a reasonably thick one. That's a bit thick. There we go. Let's see if this is. So if we have this is kind of 0 amplitude. Let's change to red. When we switch the note on, the sound is going to, the amplitude, the volume is going to rise. And the speed with which, or the time over which it takes to reach its target volume is called the attack. That's A, the attack, and that's in seconds. Then we get another portion of the sound envelope, which is the decay. So in some instruments, not all, some instruments, the sound will actually reduce in volume over a period of time, and this is the delay or the decay. That's also in seconds. Okay, and then if you keep the key pressed, then what you're going to get is a sustained level of volume. It's going to stay at that level, and that's the S part of ADSR, and that is a volume level. That's basically, we could say it's either decibels, but we're going to use a percentage of maximum volume. That's a sustained level. So it could be that this is the S is 100% and there's no decay at all. But this is a general kind of envelope that we're going to create, and then there's a release. So where we take your finger off the key, and this is the R part of it, and the note dies away over time. So this, at the moment, attack A and R, attack and release, are currently 0 seconds. So the instantaneous. S is 100% of the volume we've set, and D is 0 seconds. So this is seconds as well. So this is why we're getting a click, because we get an instantaneous attack and instantaneous release. So as we shift between notes, we're getting that little click, and I'm not sure if you can hear that in the background, but that's what's causing that. And we want to have a more realistic slope. So this could be very, very short time, but it should enable us to blend notes together when we play them together. So this is called ADSR. ADR, and it's basically an envelope. So that's what we want to kind of work with. Now what I want is our synthesizer to be kind of configurable, and we want to be able to set all 4 of those variables, and when we come to creating instruments or presets, we want to be able to preset all 4 of those variables, because that's how we can give our instrument its character. So it could be that I don't know, a church organ might take a while to build up to its notes. Its volume may increase over time. It hits a maximum and then it drops away as the kind of the pressure of the air in the pipes reaches a maximum, and then it equalizes and we get a nice sustain, and then there's often quite a sharp release on a church organ, so it could kind of swell and then release. So that's kind of characteristic of a church organ. If you pluck a string on a guitar, for example, the attack's going to be very very quick, but often, unless you damp the string, the release is going to be kind of long. It's going to kind of carry on playing. And we may want to have a sustain pedal, for example. It will be like pressing the space bar or something, so we can have dampening and sustain kind of features eventually. Those are the kind of 4 variables you want to control. But in the class that comes with N-Audio, control is only given us for the A and the R, and we want to be able to also control sustain and decay. So what I'm going to do is basically pinch a lot of this code out of here and put it into our synth sample provider class. So basically we're going to be able to control all 4 variables. Okay, so let's go and do that. Okay, so we're in our synthwave provider. Cheers everyone, by the way. We're going to want what's called an envelope generator. So this is what's going to control those 4 variables. Luckily, N-Audio comes with an envelope generator, so we can call one of those straight away. So envelope generator, and we'll call that ADSR. So that's in the digital signal processing area of in audio. If we pop over back to the code, you can see that we have attack and release here already done for us. So let's grab those out of the code. There's bass frequency. Let's put that above there. We should have done that raw, shouldn't we? Oh, mind. So we need private float attack seconds. Okay, and this needs to be underscore ADSR. So when we provide ADSR, that's up there. So when we provide a value in seconds, we're going to multiply that by the sample rate of our wave format, because that's the form that the envelope generator wants. It wants the number of samples. Feels stable. Boy, my Mac Pro almost dies from my shader. Is it proving quite computationally expensive? Then links up. Feels stable. Are you still doing those terrain generations which you've got on the Discord? Thank you, Limson, for pointing out my spelling mistake. Yes, you obviously know me well. I make loads of kind of spelling mistakes on this stream. So you're just messing around with ray marchers because you enjoy that. Yeah, I know you do. But it is about terrain. Yeah, those terrain things, those mountain terrains that are created are fantastic. So you can see how powerful that technique is. If it's almost like you say, it's almost like a random reading of a texture to create a three-dimensional landscape with all the lighting and the shadowing and the mists and things. It's wonderful. Okay, so that's our attack, and we also want to go across and grab the release code. So we'll grab that. Make some space here for it, because we'll try and put them in order. There, and that's going to be underscore ADSR, and we want to have private float that. Okay, so we've got the A and the R. So basically, we're going to want the same kind of things for the decay and the sustained volume level. So let's just change this. So this is going to be decay. How must this be? Decay. Okay, grab that. Okay, so let's make sure we got this formula correct. Let's go and have a look at the code over here. So the formula for decay is multiplied by the wave format sample rate, which is cool. And then finally we've got our sustain level. Sustain level. This is a volume level rather than number of seconds. And that's simply going to be equal to the sustain level. Okay, so now I have variables which allow us to control their properties, that allow us to control all four of those things. Okay, just checking my notes to make sure I've not missed anything. I think that's all we need. So down here we can create an instance of our envelope generator. So I'll just go ADSR is going to equal to a new envelope generator. Okay. So what we've got on the constructor, nothing at all, I don't think. So then we can set some defaults up, I think, in case we don't get anything passed in. So attack seconds, we're going to make it really quick. The decay seconds, we're going to make we'll make that 0, so no decay on this default instrument. So the sustain level, we'll default that to be full volume. That's 1.0F. And the release seconds, will default that to be a third, 3/10 of a second. Okay. Okay, and what we need to do, if we go back over to the code in the repo, you can see that we actually issue this command, which is on the envelope generator, which is gate is true. So this is basically going to initiate the forming of the envelope. So it's going to take us through the attack, decay, and into the sustain portion of the envelope, and it will stay at sustain as long as we've got the key pressed. And then we need to switch off the gate. We need to set gate to false to initiate the release phase. And to do that, we have a stop method. So let's pop the stop method in. Grab that and pop it over to the other side. So the stop method can go here. And we need to put an underscore in front of that. But when we start making a sound, we want to put the gate on. So we set that to true. So once we initiate the release phase, what's going to happen is it's going to reduce the volume down to 0. So we need to actually kind of escape from this read method when the volume falls to 0. So for you, Snowball, will you add recording so we can record and play back? Yes, I want to have some sequencing and recording and that kind of thing. So that kind of starts to bring us into other aspects of the N-Audio library, where we have recording and playback. So we kind of start to use all of the features. So yeah, we're going to have that. I'll put that onto the to the issues list as well, so that we can. And also, what I'd like to be able to do is to record like a loop, and then have that playing back while we play over the loop. I mean, it'd be great. It'd be good if I was actually a pianist. But I play the guitar a bit, but I don't play the keyboard, so I'm not really capable of holding a tune on this. But we never know. Might learn to play something. So I can play a couple of kind of a chord progression, record that as a loop, and have that playing, and then we can kind of noodle over the top of that and see what happens. But that's all kind of the plans we've got for this this whole thing. Okay, so we've got to stop. Now, because we've got this stop method, we don't really need a note on and note off anymore, because our the ADSR part of this is going to control that for us. So in effect, what we can do is get rid of this code here, and we no longer need. I think we've got a property of note on. Yeah, there. We don't need a note on property anymore. Okay. Let's go over to our source code again, and we can see here we've got a line here which basically says if the state of our envelope generator is idle, then we return 0. And whenever we return 0 as the count of bytes read, that means basically that this note is off. It's going to kind of be disconnected from our mixer. The mixer class we're using actually will do that automatically. So when it no longer gets any samples, it will actually discard that that sound source from the mixer. So that's what we need to do. Links beneath, if you could change your stream voice to a robot voice. Yeah, we can do all kinds of things. We can have voice changes and stuff like that. Yeah. Although you can download them, I think they're free, or and you can link them into your Stream Deck, but it's a bit kind of gimmicky for my stream, I think, because other streamers have lots of sound effects and voice changes and stuff, but I'm not really sure it's kind of my style. So if we grab this bit of code and we can pop that in just about there, and that's going to be underscore ADSR. And what we're going to do, I think we're going to turn that into a that format, because we may want to do other things when we've finished, like clean up some of our resources when we start to build on this class a bit more. Okay, so that'll escape us from the process, and I anticipated what we need to do here. What we need to do is actually process that sample like that. Let's just do the code tidy up on that. There we go. So what is that going to do? ADSR process is going to apply the sound envelope. So remember that the ADSR state is going to go through 4 phases. It's going to go through the attack phase, the decay phase, the sustain phase, and then eventually the release phase, at which point it will drop to the idle state and it will bail out of this read, return 0, and by returning 0 it means we've now finished producing the note. Yes, I'll sort of make a voice. I'll be back. Okay, so that's pretty much. Let's just give a quick scan through the source code. I think we're okay. So that looks pretty cool. What we need to do though is go back to our view model, and we need to kind of alter this a bit. So no longer do we have a note on and note off. The note on is no longer required there, because when we initiate our note, it's going to start the ADSR envelope, and we won't. It will no longer be idle. So we'll run into our read, and where we had if note on before, this is basically our guard clause, which is making sure that we play sound until we drop out of the release phase into the idle state, and then we stop. But we need to initiate that stop. So we need to, rather than note on equals false, we just need to call stop there. Right. So what you can see, when we press a key, we generate a new synth wave provider. Whatever base frequency we've got selected on the selector, and then we add it to the mixer. We've got a mixer which is taking all our notes. This is why we've got a polyphonic keyboard, because we're mixing many notes. We can actually mix up to 1024 different sound sources into a single mixer. We only have one mixer at the moment, but as we start to build up our presets and we start having multiple types of wave for one note, so combinations of waves, that make up one single note, we're going to have lots and lots of mixers. It's just the way we can kind of blend those waves together in a mixer. So at the moment, only one mixer. We add our input to the mixer here, and then when we lift the key up, we sense stop. That's going to initiate the release. Eventually, after at the moment 0.3 of a second, we will stop reading samples. So count will return 0, and when count returns 0, the mixer underscore mixer will automatically discard the oscillator, so it won't be connected anymore. The mixer is here. So here's our mixer. We've got a option on the mixer which is called read fully equals true, which means it's always producing samples. So it's going to produce samples of amplitude 0, i.e. silence, if we've got no notes attached to the mixer. And we've got a volume control post the mixer, so our signal chain. If we kind of describe what our signal chain is. So our signal chain currently is we have an oscillator. Oops. We have an oscillator. Which has got, this happens to have ADSR in it, rather than using the class that we had before, or the class that we saw. We're then passing that into a mixer. So we're doing that. We're passing the output of the mixer into a volume control. You've got to remember there's lots of, potentially if we're playing a chord, there are several oscillators feeding in at the same time. This is our volume, and then we're passing that signal chain into an output device. Which at the moment is Retro CRT. Thank you for the follow. 199, we're one away. Let me just reduce this and give you some Electric Alf. Thank you very much for the follow. That's wonderful. Very, very much appreciated. A nice handle as well, Retro CRT. Thank you. Where are we? So this is our signal chain. So we've got lots of oscillators coming into a mixer, into a volume control, into our output device, and this is a wave file. Wave file output. So the format is a WAV file basically, and we can record that. So yeah, we can record that, and we can do that. I'll put some issues in, and we'll do that in a later stream. So that's our signal chain we've got at the moment. In fact, the signal chain actually, you can see here, we're actually also pulling the volume control output into our fast Fourier transform sample provider here to provide the metering that we've got. So it kind of goes off. We kind of filter some of that off. Output of that also goes into our meter. So we can put a block there, which would be a spectrum analyzer and the waveform visualizations. This is usually designated with a plus sign, so that's the mixer. Okay, that's what we're looking at the moment. So let's see what the addition. We've done a bit of code there. We've added this envelope generation. The envelope is a very, very fast attack, and no decay, full volume on sustain, and then 0.3 of a second on the release. So we should get rid of that clicking that we heard, and we should have a slightly noticeable decay of our note as we play them. But what we'll do is we'll fiddle with these values. So let's bring up the synthesizer. Okay, so if we listen carefully, here's note C. So if I now play a scale, so that clicking is now gone, and there was a very, very slight, just about discernible release on that note. So let's make these ridiculous numbers. Let's make that 1 second and this 1.3 seconds. So this should be really obvious now that we've got that envelope control. So play the scale again. There's a bit more kind of church organ-y really. So let's play around with the decay. So let's set the decay to, I don't know, 1/3 of a second, and then the sustain volume to be just 80% of the maximum. So it should rise to 100%, then decay over 1/3 of a second. Let's make that actually 1/3 of a second. Decay over 1/3 of a second to 80% volume, and then have a long release. Let's see what that sounds like. You can see it dying away then when I play that chord. Okay, so we've got some control over that envelope now, so which is quite fun. So let's put these back to some default values, and let's make a control in our GUI to control that. Okay. So this is where we kind of delve into the mysteries of GUI design. So here's our form. So what we're going to want to do is have over here somewhere, we're going to want our envelope controls. Sounds like an organ. Yes, it did sound like an organ. So Audrey, thank you, Andrew, sorry, thank you very much for the comment. Yes, it does, and that's kind of the idea really. Is we can start to build up some of these sound profiles as presets, and then we can have a radio button which will be the church organ sound, and then click that, and all the various parameters will be preset to that. To give you a starting point, then you can change them, and we'll have different types of but we're quite a long way away from having voices and instruments yet, because we need to introduce things like having multiple mixers, so each note could mix several kind of waveforms together, including some of the things that we can produce in our signal generator, things like white noise and pink noise. So this is like the breathiness. So a church organ will also have that breathiness as the air kind of rushes through. It produces lots of kind of random frequencies of like white noise, which gives you that character of the sound of air blowing. Same with the harmonica. As you kind of physically blow through the harmonica, then you get lots of random noise mixed in with your notes, and that's what gives that instrument its character. So we're going to be able to do all that because if we just go over to here, where we have our key press, is this sawtooth wave here. If we look at what we've got as variables, we've got pink noise, sawtooth, sine wave, square wave, sweep, which is like a chirp, triangle wave, and also white noise. So we have, this is why I've gone for the signal generator, because the kind of mathematics behind producing things, something like pink noise, is relatively complex. We've got all that built in, but we want to extend it. it's not going to be good enough when we want to start having frequency modulation on our signals. So we have a slight variation in the frequency, which is what vibrato is. It's when, if you're a guitarist, when you apply the vibrato with your left hand on the fretboard, you're slightly varying the frequency of the note, and you have that kind of, it's a low frequency. It's 2, 3, 4, 5, 6, 7, 8, 9, 10 times a second. You're wiggling your finger on that fretted note. So it's low frequency compared to the note you're playing, which is going to be in the hundreds of hertz. Okay. Where was it? I was over in the Xamon, wasn't I? So let's have a look what we've got here. So there's the volume control here. So we've got 4 rows. So we're in row 0 and row 1 there. Our label for the volume is in row 2, and our on-off buttons, that stack panel, that's there. So the octave selector is in row 3, and then we've got a stack panel stuck underneath it. Okay. Well, let's just have a play. Let's see what we can do. So we want some more rows. So let's have what was the row that the volume control was in? Volume control is in row 2. Let's make a row 5 or row 4. Row 2, row 3. Okay. I'm trying to think find the best place to put this, because it can get a bit confusing, this kind of. So there's our radio buttons. Let's put it under the radio buttons, which is here. We've got a stack panel with some radio buttons in it. So let's have sliders. Copy the slider here. We'll make these vertical sliders. Vertical. So this is going to be in row 3, is it? No, that's in row 3. Row 4. Vertical. This binary is going to be onto attack. We don't need to do a column span. So is that what it is there? Is that it? Okay. So the minimum value for the attack is going to be 0, and the maximum is going to be, let's put 0.0 and 2 seconds, perhaps. So grid row 4, 0, 1, 2, 3, 4. Let's give it a height of 200 and see what happens. Where's my slider gone? Is that it there? Let's put another one in. So this is in column 1. Can we get just another one in? There it is. By the look of it. Appeared in a weird place. 1, 2. This is going to be our decay. So you have to kind of forgive me with this kind of design. So we're just going to fiddle around and see what happens. This is going to be our sustain. This is going to be from 0 to 1. And another slider, which is going to be in, so that was in column 3, this one in column 4, and this is going to be our release. And once again, that's going to be 0 to, I don't know, 2 seconds release. That's a very long time to release, isn't it? So where is that appearing? So they're appearing there. So I think this is the right row. Let's make this row and increase the height by 500. We've got some sliders here. They look rubbish, don't they, though? Can we fit them all in next to each other in the same? Maybe someone to do a PR to fix up my my sliders. I think maybe if we had some kind of stack panel. Let's put them inside a stack panel. This is where I get very sketchy, I'm afraid, guys. So just bear with me. We'll come up with something here. Nope, can't see exactly how to do this. I'll tell you what, let's go and get some inspiration from within N Audio itself. I'm sure that there's some code in here. Where should we go? WPF demos, equalization demo. Let's look at the XAML for that. There we go. What's that? There's a that panel horizontal grid row 1. That's what we want, isn't it? We don't want so many sliders, but we can grab that. And let's pinch that. Let's pop that into there. So this is going to be in grid row 4, wasn't it? Let's pop it in there. So there's our sliders down there. Interesting that the buttons are there, but we'll fiddle with that later. We only want 4 sliders. So the binding is going to be to attack, decay, sustain, and release. And we said that the minimum is going to be, okay, so for our attack it's going to be 0.0 seconds. 0.0, so actually that'll be the bottom one. Let's have a, no, we'll have 0. And a maximum value of 2 seconds. Once again, a decay 0.0 to 2. These are ridiculous values. This is going to be 0.0 to 1, which is our sustained volume. 1.0, and then once again the release will go 0 to 2. Uh, 0.0. Okay, so now we've got those sliders. We need some labels. Okay, so I think we need some more. We need some more rows, don't we? So let's have some more rows. A row above and a row below. Let's tidy up our XAML a bit. Okay, so we've got those. This wants to be the 200, where our sliders are. This can be auto, I think. So 0, 1, 2, 3, 4. This can be 200. This one auto. We'll move all these things around, I think, at some point, but this is going to be in grid row 4 now, so it should move it down. Oops. Grid row 5. Yeah, okay. Off the bottom of the screen again. 0, 1, 2, 3, 4, 5. We got a 6, so let's make that. Make this and 700. We've got plenty of screen real estate. Okay, there we've got a slider. Okay, so I think we need a label. I don't need a name for it. The content's going to be envelope, and that label. I think we can put labels in various places. So content's going to be that. The grid row is going to be in 5. No, 4. Yep. We want to kind of centralize that and push it down. So envelope, grid row 4, horizontal alignment, center, vertical alignment, Vertical alignment, we want it to be at the bottom. That looks okay. Can we make it bold? Sort of weight. Style. Can we have bold? Clearly not. Is it going to give me any clues? No. Didn't want to do that, did I? I like to have them vertical so I can see them all on the screen. The style is not one of them. Okay, we'll live with that. Actually, let's make that center rather than bottom. So it's at the same level as octave. And we want some labels underneath here, and we want some kind of value labels at some point, but we'll worry about that later. Can we put labels on this? So we could say A. What does that do for us? Doesn't like it. Looks like we can't put a label automatically on that slider. So we won't worry about that. Let's just not get bogged down with UI, because it's not going to be what I'm strong at. I'm a back-end developer rather than a UI developer. Okay. Maybe we could put some across the top here. Envelope. ADSR. That'll be enough. Okay. So now we've got 4 variables which we need to bind to these attack, decay, sustain, and release. So this is where FuelSnable's T4 template comes in. So we have a TT file here, and we can use this to do the binding for us. This will generate our view model for us. So let's add some more properties. They're going to be floats, but not arrays. So we want, let's line them up. So we can have attack, decay, sustain, and release. Let's run that template. Okay, so we've now got a generated view model which has changed. So let's see what the generated view model is. So we now have some new properties, I hope. There we have the attack, decay, sustain, and release. And all the on-property change methods, all that's been created for us by that template. So That's the only advantage that we've gained. All we need to do to get to kind of wire up our view model to our UI is just simply add those 4 lines there, which I think is fantastic. Okay, let's go out of here to our view model, and we've got a construction event here where we can set up some basic values. So we can basically go and get the values out of the synth wave provider here. Let's go and get these values and pop them over here as our defaults. So that's going to be attack, decay, sustain, and release seconds. Okay, let's run the synthesizer, see what happens. So we've got our presets. This is obviously very small. This range is far too large. I think that's the problem with that. We need to make that range smaller. So what we could do, let's switch our synthesizer on. Let's increase the release. So we're not wired up yet, are we? So let's go back down here. Where's our key? So here, this is where we need to do some work. So we need to say the attack seconds. It's going to equal our attack. The decay seconds is equal to our decay. We need to say that sustain level is equal to sustain, and our release seconds is equal to release. Okay, so that should wire up those variable values to our when we instantiate our synth wave provider now. So let's go and try that. Will it work? So let's play. Increase this. Let's put in some decay. Drop that down. Let's have a long attack. Well, pretty pleased with that. We need to smarten this up, obviously. It's a bit all over the place. This could do with being over here and stuff, but you know, I'm not overly worried about getting a smart UI on stream. I can tidy that up off stream. That's looking pretty good. Now with the sawtooth wave, one of the things that that comes with a sawtooth wave, as kind of pointed out to you, with that frequency analyzer we've got, the spectrum analyzer we've got now, you can see there's an awful lot of harmonics generated, a lot of high frequency harmonics, and that's not necessarily a great thing. We want to kind of mellow things out a bit, really. I think this is the next thing on my notes that I want to look at. So let's just do that. So the way we can deal with all those high frequencies is to filter them out of our signal chain. So once again, if we go and look at our signal chain, what we can do is, before we go into the mixer, we can put a filter in here, which by default when we first start off, it's going to be there all the time. We're going to filter out our high frequencies, but then we'll have it so it's variable. So initially we'll have it say on and off, and then we'll have the kind of cutoff frequency and the steepness of the cutoff be variable. That's more sliders and buttons and things. So I think initially what we're going to do is just have it in there all the time, and hopefully be able to see the difference on our frequency analyzer. So let's have a look at doing this. We're going to need a new class. So let's have a new class. And this is going to be a pattern that we're going to come across over the next several streams. We're going to add something into the signal chain. We're going to add a custom sample provider. This is going to be a low pass filter. Low pass filter sample provider, we'll call it. Okay. Let's make it a public class. We want to implement iSample provider. So all of our effects that we're going to build for our signal chain are going to be this interface. If we look at if we implement that interface, you can see there's two parts to it. There's a wave format and a read method, and that's what we need to implement. Now, luckily, the whole kind of process of doing filtering is mathematically quite complicated. There's an awful lot to it, but luckily within N-Audio we have some helpers. So if I go up to where shall I go to? I think it's going to be in the DSP, the digital signal processing area. DSP. We have something in here called a biquad filter. This is implementation. It's based upon something from Music DSP, which I'm going to be telling you about a bit later on. But it's a website where a lot of open source algorithms have been kind of collated, and there's algorithms for all kinds of filters in there. And what Mark Heath has done here is he's built this biquad filter class. And what it allows us to do is to create a low pass filter, a high pass filter. Here's the low pass one. There's a high pass filter, something called a band pass filter, which is like a notch kind of idea. There's a notch filter itself, an all pass filter, and a peaking equalizer. So these things, I'm not telling you that I know what a lot of those things do, but because that's future reading for me, there's an awful lot of complexity to this subject. But what we're interested in doing now is filtering out some of those high frequencies to try and mellow out the sound a bit, because especially with the saw wave, it's very, very harsh. So we're going to implement a low pass filter. It's going to be really easy because we've got this biquad filter class to base it on. So this is what we need to do. This is going to take in three values. The sample rate, which is, as we know, is 44,100, has to be the same across our entire signal chain. We need a frequency which we're going to cut off. So we're going to say above this frequency we're going to apply the filter, and something called a Q. And Q is, I think, if I was to kind of paraphrase what it is, it's like how aggressive that cutoff is. It's the steepness of the cutoff curve. Is it going to be really, really kind of aggressive and cut off, drop down really vertically to zero amplitude above that frequency, or is it going to be more of a kind of gentle curve? So with the value of Q is going to determine that. We're just going to set some default values in initially, so we can kind of get a feel for what it does, and then eventually we'll build some UI elements which allows us to kind of fiddle with those and change them on the fly. So the low pass filter is going to be relatively easy to build. So when we deal with these effects, there's basically we need to have a source, so that we're going to put a source in, and then a read method is the output. So we're kind of plugging the blocks together. So the idea is this coming in is the source, and then the read method provides the output. Here's my writing. Okay, so that's how they plug together in our signal chain. This is exactly the same. I've got on the floor down, I can't actually reach them on the floor. I've got my guitar pedals, and there's an input and an output and a pass through. and that's the kind of idea. We could have situations where we could kind of go like that if we wanted to. We don't have that, but we could do. And we can also have feedback where we might take some part of the volume and feed it back, into something like that. Feedback loops. And we're going to be looking at that kind of thing when we do delays. Like a nice echo kind of effect that's going to involve feedback. Okay, so let's implement this. So first we need a source. So we're going to need a private read-only iSample provider. That's iSample notifier, iSample provider, which is going to be source. And we need the filter. So we need private read-only. This is going to be a bi-quad filter. This is going to be a filter. Okay, let's bring that namespace in. So if you read around the subject of digital audio, this concept of the bi-quad filter is relatively prevalent, and it's really good that N-Audio provides a built-in class for it, because we don't have to worry about that implementation. This is going to simply return the source.wave format. Okay, so we need a constructor. So public low pass provider, and we need what do we need? We need to pass in a source, which is going to be an iSample provider. We need to pass in a cutoff frequency, and we're going to default that to 4000 Hz, just as a number to think of. And then we need a float, which is going to be the Q value, which we mentioned, and we're going to default that to 0.7. Just numbers pulled out of the air. So then we're going to set the source up, and we create a bi-quad filter. And bi-quad filter, so we don't need a new, we can use the static method. So there was a static on there, which was low pass filter, so we'll use that, and we need to pass in those values, the sample rate, the cutoff frequency, and the Q into there. So that is low pass filter, and the sample rate was be the source dot wave format dot sample rate, and then the cutoff frequency and the Q. What's it complaining about there? Cutoff frequency does not exist. Cutoff frequency, that's okay. Okay. So we've got ourselves a constructor, so we've got our basic objects set up. So we've got a filter and we've got a source. So now we need to implement this method. And once again, this is kind of this is going to be the pattern that we're going to be going through every time we create a new effect. We're basically going to pass in a source, maybe some of the values. We're going to create whatever we need to create in our constructor. Then we're going to process in the read method. So the first thing we need to do is read the samples out of the source. So very simple, similar to what we did before. This is going to be source.read, and we're going to pass in the buffer, the offset, and the count. So now we've got our buffers, and we're going to basically return the number of samples we read. In between there, we need to do the actual processing. So we're going to have a nice little for loop, and it's going to be that's going to be samples. So the number of samples we've read, and then here we take our buffer, and it's going to be the offset. And this is, once again, it's got just a pattern plus I, and we're going to process that. That's going to be processed by the filter, and we've got on here on the filter we've got a transform method. So we hit that, and we pass into that the buffer, offset plus I. So that's basically all there is to the low pass filter. What it's going to do for each of the samples in the buffer, it's going to process it through the transform method of our low pass filter, and if it's above 4000 Hertz, the frequency of that sample, it's going to apply the low pass filter, and this is the aggressiveness of the cutoff, which is not very aggressive at the moment. I think it's basically what it is. It's fairly gentle. Okay, so we've got a low pass filter implementation. It's basically there's very little work we've had to do. All we had to do is implement the transform method and process our samples against that. Okay, well, that's where we're going to put that in the where are we going to put that? I think we need to put that pretty much at source. So off in our view model, this is our note. So what we can do, we can create a new low pass filter. And we can simply pass that as our source, and then we've got all the other defaults. We've got the 4000 Hertz cutoff and the 0.7 value of Q, which is to say it's the aggressiveness of the cutoff curve. So we should be able to see this. So what we'll do is I'll stop that. I'll just copy this line, and we'll see what it looks like with and without the filter. So let's just remove that. Once again, we'll copy that, we'll comment that out. We're going to run with a sawtooth wave switch on, and if we look at the high frequencies at this end, as we start playing some notes, what I'll do is I'll go to the middle octave. Well, let's play the note C. See the high frequencies here. Here's the fundamental. Lots and lots of harmonics. So let's have a look at what happens when we put the low pass filter into there. And honestly, I don't know what's going to happen, but I'm hoping it's going to cut out a lot of those high frequencies and kind of mellow out the sound a bit. So this is the same note C. Let's choose the middle. So it's no longer as harsh. Can you see there's not so many harmonics in there? Here's the fundamental, and there's still some harmonics. Let's switch that off and compare that again to without the low pass filter. It's a much more pleasant sound, I think, with the low pass filter in place. And this is what you tend to find, is that you can really kind of shape the sound of your instrument by using these filters. And we can do a high pass filter as well. In fact, we'll do one. We'll write one. It's no more difficult than what we've already done. Perhaps we won't use it at the moment, but we'll write one. So here's without the low pass filter. Much more buzzy. It's hard to credit it's the same sound actually. It's quite, once again, with the low pass filter in place. When you play the chord, the kind of buzziness comes back, but it's pretty good, that, I think. So we've got a low pass filter in place. What we want to be able to do is control that. So we'll leave that line commented out. What we want to do is to have a tick box, I think, on our form, which says whether we want to have the low pass filter in place or not. And then we'll want controls to control the levels. Let's quickly write a high pass filter. It's basically we can copy the code. High pass filter sample provider. And we'll just go and grab the code for low pass filter. High pass filter. Putting some namespaces in. We can make this suitably low. I don't know. I don't know. And this will be a high pass filter here. And there we go, that's a high pass filter. So we've got a couple of effects. We can plug those in and play with them, see what happens. Right. So I thought the other thing we could do would be have a tremolo. So a tremolo, this would be our kind of first proper effect. It's a very simple effect. This is a volume modulation. So we're going to modulate the volume of the overall sound. So tremolo is pretty basic and simple effect, but we're going to use these ideas that we're kind of creating with the simple effects to build up to more complicated ones where we have a lot more maths to do. So let's create another class, and we're going to call this Tremolo sample provider. Tremolo, that's it. Make that public. Public. And once again, we're going to implement the iSample provider interface. Bring the namespaces in and implement it. Okay, so this is very, very similar to what we had before. So we need a private read-only iSample provider, which is going to be the source. Read-only this here is going to throw out source.waveformat, and we're going to do some things in here. We're going to have var samples equals source.read, and pass in the buffer, the offset, and the count. The count being the number of samples that have been requested by the sound card, basically by the sound, by the wave file out device that we've got, which basically can be the sound card. Okay, and we want to return samples. That's the count of samples. So we've got the basics there. So almost we could create that as a template. I could create something along these lines in CodeRush as a template, which might be fun to do. I might do that. Okay, so we're gonna use this this tremolo control to actually vary the volume or the amplitude of all the waves that come into it. So we're going to it's going to be the mixed output. So we're going to need an oscillator, a simple sine wave oscillator, to which is going to provide the variance. It's going to oscillate between some small numbers like 0.2 and minus 0.2, and that variance is going to be applied to the input volumes. So we need a low frequency oscillator. So this low frequency oscillator isn't going to be used for frequency modulation. This is amplitude modulation we're going to be doing. The frequency modulation is slightly more complicated, and there's an issue on the GitHub. If we go to our GitHub, here, about some frequency modulation. If someone, I'm assigned to that, but if someone wants to kind of tackle adding frequency modulation, that would be fantastic, as if you want to kind of help out with the project and submit a PR. Okay. Read only. This is going to be a signal generator. It can be an I-sample provider actually, because signal generator is one of those. And this is going to be a low frequency oscillator, LFO. Okay, so let's create a sort of constructor. So public Tremolo sample provider, and we're going to pass in an I-sample provider as a source. That's probably all we need at the moment. We were going to want to be able to control the tremolo at some point, but let's just get a basic tremolo thing working. So source equals source. So let's set up our source. Now the low frequency oscillator we're going to need to create. So let's have it pass in an int, which is going to be the LFO frequency, and an int which is going to be the LFO amplitude. Okay, so we want to create a new signal generator. A new signal generator, and this is going to be the sample rate, which we need to kind of sort out. We need to have this is going to be the source dot waveformat dot sample rate, and it's going to be one channel. So that's probably the source dot waveformat dot channels. Yeah, there we go. I need to bring that in, and then we can set the type is going to be a sine wave. So that's signal generator type.syn. The frequency is going to be equal to the low frequency oscillator frequency. The gain, which is the volume or the amplitude, is going to be equal to the LFO amplitude. Okay, so that sets up our low frequency oscillator. So we'll set some defaults. We'll set 5. This is the rate at which the volume is going to be modulated. So 5 times a second seems reasonable. We want quite a small number for this, so we can default it to 0.2. 0.2 perhaps. This is going to be a float. 0.2. So 20% variation in the volume. That should be noticeable. They're good defaults, I think. We can always fiddle with them if they're not good enough. So we want what we want to be able to do now is to say LFO.read, and we need a buffer, LFO buffer, and then the offset and the count can be whatever got passed in. We need a separate buffer, don't we? We'll declare that. Declare a local. And that can be just that. That's going to be a new float of size whatever the count we've been requested. We can make that var. Okay, now we can do the usual thing where we kind of step through all the samples we've collected, and we need to process them. So once again, it's similar to the last time. We're going to have buffer offset plus I. Here we're going to add or subtract the variance, the 20% variance that the low frequency oscillator is providing us. So here what we can put in is we can put this value. It's going to be a plus there. Most often the offset is 0, by the way. So it's just buffer I really, and we're going to multiply by the LFO buffer, the amplitude of the LFO buffer sample at that point. Looks like we can get rid of that. Okay. So what that's saying is take the sample at this point in the buffer, and then multiply it by the low frequency, the amplitude of the low frequency oscillator at the same point, and then add it in. So it could be positive or negative. So this could be a positive or negative number. So basically what we're doing is we're varying this, and it's a low frequency oscillator. Remember, this is going to be, I don't know, if we're playing the note of A in the second octave, that's going to be 110 Hertz. But our low frequency oscillator is defaulting to only 5, so only 5 times a second. So it's a very kind of subtle effect. And what we're going to have to be able to do is to switch this tremolo feature in and out of our signal chain. So our signal chain is going to have, after we come out of volume, we're going to put our tremolo in here. Okay, but we won't better switch it on and off, so pull it out and push it in. So that'll be for another stream, I think, when we smarten up the user interface, and then we can select what the frequency and amplitude of the LFO are, and actually switch the tremolo in and out. But for now, just for testing this, let's just pop the tremolo filter in, tremolo effect in. So okay, so we've got a volume control here, which is taking in a mixer, and then our wave out, our player, is taking in FFT provider. Okay. So what we can do here is we can create a new tremolo. So this is going to be a tremolo sample provider, tremolo. And down here we can say underscore tremolo. Did I call it underscore tremolo? Yeah. That's going to be a new tremolo sample provider, and into that we're going to pass volume. That's underscore volume control. And what we'll do is we'll have a version of this. We'll copy this, comment that out, and we'll pass in underscore tremolo into the fast Fourier transform sample provider, which does our spectrum analysis for us. Okay, so let's try that. So we should now get that kind of tremolo effect when we play. So let's play the note C. So you can hear that variation on volume. So that's 5 times a second, 20% change in the volume. Which is quite a nice effect, really. So that's the kind of the first really of the simple effects that we've created. And it's pretty much brought me to where I wanted to be. Let's go and have a look at our issue list. So ditch wavetables in phase of signal generators. We've done that. We can close that issue. So we added ADSR envelopes. We can close that one. So we did delay, attack delay, sustain and release control. And we put a UI in there, but we need to smarten that UI up. So I'm going to leave this open. Need to smarten up the graphical user interface, put the ADSR envelope code is in place. So we'll leave that open. If someone wants to finish that off as a pull request, be my guest. Just let me know in Discord. Here's my Discord. Let me know if you're interested in claiming that, and I'll mark it, and you can do that. So that's that one. So we'll leave that one open, apart from that change to smarten up the UI. Low pass filter, we've done that. We've implemented a low pass filter. Also created a high pass filter. Yeah, so we've got that. So we can close that issue. In fact, no, we'll reopen that issue. Say, oops, what we do there? I'll just stop me bot, haven't I? Have I stopped me bot? Yeah, I'll start the bot again. Sorry about that. I've lost my GitHub. Tell it's getting late. Synthesizer issues. Low pass filter. So we say need to add on off control and controls to vary cut off frequency and value of Q to the GUI. So I had that comment. Okay, so that's something more to do. Tremolo effects, very similar. Need to add GUI controls on off LFO frequency and amplitude controls as well. Okay. Anything else? So I think that's everything we needed to do. We've achieved everything that I've set out to do today, so that's pretty good. So tomorrow we'll have a look at some more of these issues. We may work on some GUI, or we may have a look at. I think we need a waveform selector. I was thinking maybe we could look at the sub-oscillators as well. So sub-oscillators is where we can enrich the sound of our instrument by not only when we play a note, at the same time we mix in that note 1 octave lower to give it a bit of depth and richness. That means the low notes will be really low, but it won't be at full volume. The second wave will be at a lower volume, and we can use mixers to do all that. And it means we do that right at the start of the signal chain. So everything else we've built, the volume control, the tremolo, the low pass filters, and all that kind of stuff, will kind of come along for the ride, really. Some of these are more difficult. So the graphic equalizer, it's a more difficult piece of work to do. LFO I need to think about, but we probably do something with that. We need to use our own class rather than using signal generator for that. But we can pinch most of the code out of the signal generator, I think. The phase shift, we can have a look at some code for that perhaps, and the echo is quite complex. So some of these, if you fancy taking a stab at that phase shifter, for example, there's a couple of resources which I'd like to point you at, especially if you are interested in any more of this kind of digital audio processing that we're doing. We're just scratching the surface and hope to build up. There's a site called musicdsp.org, and what this is, a whole kind of collection of articles that people have submitted with their algorithms for doing a lot of this work. So for example, in filters, you can see there's a whole bunch of different types of filters, including some quite complicated ones. But here's a low pass filter, for example, and there's a file that's linked into it. But some of these have actually got all the codes. There's a pink noise filter with codes and stuff like that in it. Let's find a better example. All pass filter, that's the explanation. Bass booster. Yeah, it's a bit of code in there. So this is probably C code, C++ code, or whatever. But a lot of these kind of algorithms we can translate into C# or whatever. and play around with them, so we don't have to understand necessarily all of the mathematics involved, because it can get extremely complicated, especially where we start getting to complex numbers. So the fast Fourier transform thing involves complex numbers, and so do other parts of digital audio processing, and it's where you need your math skills. So if someone's done the work and come up with an algorithm which works and has been shared here, it makes sense to use those open source algorithms rather than trying to build them yourself. For some complicated effects, it may be required that you sit down with a kind of a component diagram and all the mathematical formulae and work it out, but it's a good place to look for here first. There's another resource called EO Level Engineering, which is a series of blog posts. This guy also provides code on many occasions in C++, and it goes back a long way. So there's lots and lots of kind of stuff. Lots of articles on different kind of subjects include, and so a lot of them do include code. So another valuable resource to check out when you're looking for algorithms to convert over to the language of choice for yourself. So I'll be looking at these two websites to figure out how to do some of those filters and those digital effects. Once again, also worth going over to NAudio and looking at some of the code in here. So, for example, for the biquad filters here, you can see that there's a lot of mathematics involved in doing this kind of stuff. But it's all broken down into relatively simple stages here. So it gives you the mathematical equation and then breaks it down so that you get what actually processes that for you. So well worth checking out the source code. One of the great advantages, of course, of having all this open source. Okay, so that's the resources that I wanted to mention. Let's push the code we've got up to GitHub. So what have we changed? Let's have a look. Okay, so we've updated our generated view model and our T4 template with our new properties. We need to go back and do some more GUI work. We've got our high pass and low pass filter, but only the low pass filter is actually used. We've updated our GUI a little bit. There's our view model. We've got updated our synth wave provider, so we pulled out the wavetables and put in signal generators in preparation for eventually creating our own signal generator class. And we did our first effect, a very simple volume tremolo effect. It's not bad going for today. So let's commit that with a comment of episode 36. Commit that in, and then let's sync that to GitHub. So if you're interested in looking at the code, forking the repo, providing some CRs, pinching the code and using it for your own nefarious purposes, feel free. That's what it's for. That's why we do the stream, and that's why it's all open source. So there's my GitHub. If you've got questions, if you want more information about links, if you want to volunteer to do some PRs on this project, then talk to me in GitHub. In Discord. There's your personal invite to my Discord. YouTube. On a YouTube channel, got all 35 previous episodes are up on YouTube. Do subscribe if you visit. It's free to do so, and it really does help me out. We're currently on 199 followers. If there's anyone viewing who hasn't followed, who can find it in their heart to follow the channel, we'll hit our 200 follower goal for this period. So that would be very, very kind of you. We've always had very kind souls who've already either subscribed or followed the channel. So if there's anyone out there who hasn't followed, then it's the best way to be kept notified that when I go live. Having said that, you can also check out Twitter. So do follow me on Twitter, if I can spell Twitter. Here's my Twitter channel. Follow me there for information about pop-up streams. Now the next stream will be tomorrow. It'll be the early stream at 4 o'clock in the afternoon UK time. That's 3 o'clock UTC in the afternoon. And more than likely there'll be also a Thursday stream, probably about 4:30. But keep an eye on Twitter and on Twitch for details if that stream goes ahead. But I'm pretty sure I'm going to go ahead with that. We're going to be continuing with this project to try and build out the GUI a bit. As I'm trying to build up my WPF skills. I'm kind of floundering around with it at the moment. So it's the very first project I've ever written with WPF. So I'm not at all familiar with what I can do, but it's starting to come together. And that's pretty much all we need to cover. Get rid of that. Okay, so we've pushed up to Git. Let's find someone to raid, shall we? Let's close some of these down. If anyone's got any preferences of who we raid, let me know in chat. Otherwise, let's go over to Twitch and see who's on at the moment. Oh, the Michael Jolly's on one of his marathon streams, I think. So we go and should we go and raid Michael Jolly? I think. If you've not seen Michael Jolly's stream before, do please subscribe or follow his channel. It's quite amusing. Okay, so let's put in the Michael Jolly in here. So thank you very much for everyone who's watched today. Chat has been really quite lively. It's a bit tailed off towards the end of the channel, but we're all getting tired, I think, this time of night. So thank you once again for your participation and for the kind subscribes and follows that happened. It's really, really kind of gratifying that happened. So I'm going to give you some hyperspatial hype for the followers and the subscribers. So here's our Infinite Alfs. This is a WebGL shader that our friend Fuel Stable created for the channel. And also we'll have some Electric Alf, another shader. So this is for all the viewers who stuck through this digital audio programming stream. So I know some of it can be quite involved, but I think we are getting somewhere. So let's do this raid and stay on the channel for the raid. We're going to see Michael Jolly. Take care, everybody, and I'll see you tomorrow at 4 o'clock UK time.